Okay, so let's talk about independent events. To motivate what we're actually going to be exploring here, let's think about rolling two six-sided dice. So our experiment will be rolling two, and we're going to suppose they're balanced. Now each one, you can roll a 1 through 6 on each. So the sample space is going to be the combinations. So sorry, sample space, not multiple, of pairs A comma B, where A and B can be 1 through 6. So we're looking at things like rolling a 1 and a 2, or a 2 and a 1, or a 4 and so 2 4s, right? So each of those is possible. So we understand intuitively that when we roll the six-sided die, that the first roll doesn't affect the likelihood of the outcome on the second roll. So we know that from intuition, from experience. So what we're saying, though, is what we get for A shouldn't affect the likelihood of what we get for B. And you can suppose that they happen simultaneously or one after the other. But let's examine this for a specific event. So let's suppose we have A is the event in which first roll lands on 2. B will be the event that the second roll also lands on 2. So let's think about these events precisely. So the event in which the first roll lands on 2, that just means the first, so A is 2, but B can be anything. It could be 1, it could be 2, it could be anything between 1 and 6. Similarly for B. The second roll, so B has to be 2, but A can be anything between 1 and 6. What we want to show, so we want to show that the probability of A, given we know B has occurred, is just the probability of A again. So B occurring won't change the likelihood of A, and vice versa. So first, we need to find what's the probability of A. So the probability of A is the number of ways to roll 2 for A divided by the total number of possibilities here. Now, you can set up a little table if you'd like to determine the exact sample space for this set. But you could take my word for it for right now that there's going to be 6 possibilities for A and 6 possibilities for B, so there's 36 total possibilities. And the number of ways you can roll 2 for A, remember, you have... so if we write out the event A explicitly, what we're talking about is 2, 1, 2, 2, 2, 3, and so on to 2, 6. And there's exactly 6 ways to do that. So 6 out of 36, and that reduces to 1/6. so that's the baseline likelihood that we get a first roll landing on 2. And now we want to see what happens when we condition on B. So the probability of A given B has occurred is explicitly what we're saying is that this is the probability of rolling a 2 for A when B equals 2. So we know the second roll is 2. So in other words, we're looking at the number of ways to roll 2 for A and B equals 2 divided by the number of possible rolls, so getting B equals 2. And so when we examine this, how many ways can we get the second roll to be 2? Just like with what we calculated for probability of A, there's 6 events in that set. So our denominator 6. And how many ways now can we roll a 2 for A and the second roll is 2? There's only one possibility there, 2, 2. So that's 1/6. So these are equal. And conditioning on B didn't change the probability. So, in other words, regardless of what the second roll was landed on, the first roll has a 1, we can also say 1 in 6 chance of landing on 2. And so what we're actually saying here is we're saying that these two events that we chose are independent events. Whatever we get on one roll, it won't change the probability of the other roll. So how do we formalize that? So what we're saying then is, so you can consider this a theorem or a definition if you want. So A and B are what we call independent events if the following two statements are true. So 1, the probability of A given B is equal to the probability of A, and 2, the probability of B given A is equal to the probability of B. One important thing to note here with conditional probability that I think may have escaped my attention earlier, it's common to confuse or to think that these two things are the same, but the probability of A given B is not in general equal to the probability of B given A. This is sometimes called the confusion of the inverses, but if you are ever confused, make sure you say it out loud what that probability is actually saying. So the probability of A, so probability of A given B has occurred is not the same thing as the probability of B given that A has occurred in general. So just a note, avoid this confusion. But for independent events, what we're saying is that the conditioning doesn't matter. They're just equal to the original probabilities. And that will be really helpful for when we want to determine whether events are independent or not. This is kind of a checklist. So they're independent if these conditions are true, and if not, then they're not independent.